Hey guys, we're going to go over question 1.53 in this how-to video. So this is the question here. Essentially, we've got a surface mount transistor. It's on a circuit board, and the board's temperature is this 35 degrees C. There's air around it, and it's going to flow over the surface of the transistor itself. And then there's 3 wires coming off of the transistor onto the board. Underneath the board or underneath the transistor, there's a little gap here, and it's going to be filled with either stagnant air, which is in part A, or conductive paste. So we're going to be looking at both those cases. And then we also want to create a plot. This is the fines over here. We want to create a plot for the amount of energy dissipated when the conductive coefficients from the leads are either 200 or 400 watts per meter Kelvin. So as a summary, we're given these variables here, and we're asked to find these 2 things. So we want to find the case temperature when there's stagnant air in the gap between the transistor and the board, and when there's thermal paste in that gap. So those are defined by having a conductive coefficient of either this 0.0263 watts per meter Kelvin or the 0.12 watts per meter Kelvin. There's a couple assumptions that we want to start out with. We know that this is steady state. The temperature is not changing with time. There are constant properties. We have an isothermal case, and we're also going to neglect radiation in this problem. To start out, I wanted to draw a little schematic of what's going on. So we have our transistor here. I'm calling this our control volume. It's the entire body of the resistor, or the transistor. There's 3 leads that are coming off of it, 1, 2, 3, and these each have a certain cross-section and a certain length, and they're attached to the board, which we know is set at 35 degrees C. And then, of course, underneath the board, there is more conduction that's happening. And above the board, we have convection, where air is flowing over the top of the transistor with a certain convective coefficient of 50 watts per meter squared Kelvin. So to start out, we have the energy balance equation, where energy stored is equal to energy in minus energy out plus E dot generated. And we're given that the transistor is generating 150 times 10 to the minus 3 watts. And we know that there's no E in, and it's steady state, so E stored is 0. E dot out is equal to 3 times QCD plus QCD2 plus QCV. So QCD is the conduction. We have 3 of the leads leading off of it. QCD2 is the gap here, and QCV is the convection due to the air. Each of these are defined by these equations here. So we have our conduction is Ka over L times delta T. And filling in the variables here, we get that conduction of the leads is equal to this bit here. And then for the gap, we're going to start out with K is equal to 0.0263 watts per meter Kelvin. And so we're given this formula. We'll plug in K is this or this, depending on if we have air or thermal paste in that gap. And then we also have convection here, where we have HA times delta T. That gives us this formula here. So what we're looking for is this T. We want to know the temperature of the transistor. So we're going to plug all of these in to the energy balance equation here. So we've got our energy generated over here, as well as each part here. So we've got the conduction due to the leads of the wire, the conduction due to the material in the gap, and then the convection here. And we need to balance these out by solving for TT. And this can be done in a few ways. If you can just use a calculator if you wanted to, but I started out with K is equal to 0.0263 and solved for this TT and got about 320 Kelvin or 47 C, and plugging in K is equal to 0.12, I get that TT is equal to 313 Kelvin or around 40 C. Now, the second part of this problem is asking us to plot the energy dissipated for various H values between H is equal to, or between 50 and 250 watts per meter squared Kelvin. And so what I did was I went into MATLAB and I wrote a little script where I defined what the K was going to be. So I wanted us to do for K equals 1 and K equals 2. And then I set H between the range, and I just incremented in units of 50 because they're linear plots. And I simply solve for each one of these variables and the energy dissipated when plugging in this vector for each of them. That way I was able to plot H by E dissipated 1 and H by E dissipated 2 to get this plot here, where on the x-axis you have the convection coefficient, or H, between 50 and 250, and on the y-axis you have heat dissipated in watts between 0 and around 0.7. And then we have two linear plots here, so K equals 200 and K equals 400 in red, that are increasing slightly as you increase H. And so that is my solution for question 1.